welcome back, everybody. So, uh, yesterday at the end of lecture, so we had talked about choosing the in this new terminology that I introduced at the end of lecture, we had talked about choosing the principal branch of the log. And so, just to give you a quick reminder, what or how branch was defined here. A branch of a multi-valued function is any single valued function, big F, that that is analytic in some domain at each point z, of which the value big F of z is one of the values of little f. So the fact that little f is analytic, and we're requiring that this big F be, or I should say, the fact that we're requiring this big F to be analytic means that the way that it takes these values, little f, it's not just going to be some random thing here. And so the easiest example of this is the one that we saw yesterday of the what we're going to call the principal branch of the log. So this function big L log of z we found to be the natural log of little r plus I times capital theta, which was the principal value of the argument, right? So this was little r is positive, and theta is taken to be strictly between pi and minus pi. Okay, this is called the principal branch. Okay, so this is the principal branch of log z. Okay, this is an example of what I mean when I talk about branch. Okay, so some more terminology here. So a branch cut, okay, is a portion of a line or a curve. So a branch cut is a portion of a line or curve that is used to define a branch of a function. So a branch cut is a portion of a line or curve that is used to define a branch big F of a multi-valued function little f. Okay. So I'll do an example after this, again involving log, to show exactly what it is I mean here. But the first thing to note is that these points on the branch cut are actually all singular points. So the points on the branch cut are singular points of big F. Okay. And any such point common to all branches is called a branch point. Okay. So, one of the better examples of exactly this type of thing here is the following. Okay, so let us consider the branch cut for principal branch of log z. Okay, so what does this look like in picture so that you can actually see kind of what's going on here? So if I'm looking to define the principal branch that I had before, right? So when I write the principal branch of log, this is defined, as I just had written, as the natural log of r, which is a real number, plus I times the principal argument, big theta, right? So little r is greater than 0, and theta is strictly between minus pi and pi. So I mentioned yesterday that we choose theta strictly between pi and pi here because if I am looking to, if I am actually looking to define a branch of the log instead of the principal branch, so a general branch, so recall a general branch of log z is defined in the following way. So the way that we did this was is given as log z is ln of r. So this is ln of r plus I theta, where r is greater than 0, and alpha, or theta, I should say, is strictly between alpha and alpha plus 2 pi. Okay, for some real number alpha. Okay. Actually, alpha didn't need to be any real number works here. So yeah, let me just have it be fully general. Okay. So then, choosing alpha to be minus pi, right, gives us exactly the principal branch. Okay. And so, in general, though, if I'm defining a branch of log z, I have this ray determined by theta is equal to alpha, right? So I have this ray, and I'm going to, maybe I'll use a different color here. So I have this ray that is theta is equal to alpha. Okay. That is telling me when I am at, angle measurement alpha here, measured from the positive x-axis. Okay. All right, and in defining this branch, this ray is the reason that it's dashed is because it's not included, right? These inequalities are strict. Okay. And so, what would happen if, say, one of these inequalities was not strict? What gets included here is, well, this ray. Okay. Why is that a problem in this definition? Right? Why is it that we don't include the ray here? So note, if theta is equal alpha is included in the domain of definition for this branch, then what is true? Well, the problem is that in this case, right, if I include values here, this function is not continuous there. It's not continuous at those points. Right? This branch of log z would fail to be continuous at those points. Okay. Why? So let's say that we try to include this ray. Okay, in the definition of this, let me box this. What's the problem? Well, if I pick a point here on this ray, right, what is the problem? The problem is that as I approach, right, as I get arbitrarily close to this point, there would be values where if I'm looking at this, so I have, if I think of this as being u and v here, right, so u is ln of r and v is theta. The problem is that I'm wrapping around, right? And so as I'm getting close to this point, okay, from either side here, I would have values that are very close to alpha plus 2 pi, but also arbitrarily close here, I would have values very close to alpha. There would be a discontinuity, there would be a jump here, okay? And we could get rid of that jump if we just don't include these points, okay, as well as the origins. So the origins are included here, and these points on this ray, that are denoted in red, are not included. Okay, that means for the principal branch, where are my points that are not included? Right, so I said that I took alpha to be minus pi here. So the ray that's not included is the negative x-axis. Okay. Okay. So if I get rid of this ray, it's continuous, and not only continuous, it's actually analytic everywhere else, right? And so this is an example of a branch cut. Okay, a branch point then would be the origin here for this thing. Okay, and so this is an example of a branch cut. The origin would be a branch point in this way. Okay. So, what's the deal with what we're doing? I mean, when you boil it down simply, our goal is to take this complex valued function log z that is multi-valued. Okay, so it has a bunch of different values, but we want to do calculus type stuff with it, right? And having multiple values is not very suitable for that. So we want to be able to deal with a portion of it that has single values. Okay, one nice canonical way of doing that is picking this principal branch. Okay, but it is important to note that when you do that, it's not something that comes free of consequence. There are things that happen when you do that that cause some of maybe the properties that you might want to be true to kind of break down. Okay, so here's an easy example of that. So choosing a branch does come with a cost, however. Okay, not always, depending on the context. But it's something that you have to keep track of, nevertheless, right? Sometimes you're going to be happy, and sometimes you're going to be less happy with the things that happen. Okay, and so let's use the principal branch of the log. So let's use the principal branch capital log z of log z. Okay, what is the principal value of the log of I cubed? Okay, what is this? Well, I cubed is the same as minus I, so this is capital L log of minus I here. Using the definition of our principal value of log, this is natural log of 1 minus I times pi over 2, right? So this is natural log of 1 is 0, so this is minus I times pi over 2. Okay. But note that 3 times principal log of I cubed is 3 times natural log of 1, minus, or I should say, sorry, this is not the quantity that I wanted to compute. I'm trying to see whether or not this log rule for the power of a complex number actually works out. So sorry, this is not what I wanted to compute. 3 times log I is 3 times ln of 1 plus I times pi over 2. Right, since this is log I instead. Okay, but this is just I times 3 pi over 2. Right? Well, if we are interpreting these things as angular values, right, well, then suddenly we're happy with this interpretation. But of course, we're not. We're thinking these are just complex numbers, right? And as complex numbers, these are not the same. These are different. Okay, and so thus, the principal log of I cubed is not equal to 3 times the principal log of I. So that familiar log rule involving exponents is not true when we take the principal branch here. Okay. However, but some log properties do carry over. So they actually do carry over. Okay. But we must be careful. When taking branches of log. Okay. So in general, we just have to be careful with how this is done. Okay. So, what types of properties am I looking for? Well, if I just refer to log, that is not referring to any branches, then if I look at the log of z1 times z2, this is indeed equal to log of z1 plus log z2. Okay. Now this log is a multi-valued function. So how do we deal with a statement like this? Okay. Note we interpret this identity in the same way that we interpreted the similar identity involving the argument. So recall, we had the following identity involving argument. The argument of two complex numbers multiplied was just the sum of the arguments. And the way of thinking about this was that specifying any two values here specified the third, right? So specifying any two values specifies the last. This was our way of interpreting this boxed property. Okay. In fact, we can actually ultimately derive this expression pretty much from this boxed identity involving the argument. And the way to do that is to look at the following properties, right? The original log properties, that you're used to from calculus. So namely, that if I'm dealing with the natural log of the real number, that's the modulus of this product, well then I do know that this is my result, that the natural log splits up in this way. Okay. And then if I look at the expression natural log of modulus of z1 times z2 plus I times the argument of z1, z2, this is, I can break the natural log up in this way, but I can also break the argument up using this expression here. And so doing this, this is the natural log of modulus of z sub 1 plus I times the argument of z sub 1 plus natural log of modulus of z sub 2 plus I times the argument of z sub 2. Okay. But then this expression is log z sub 1, and this expression is log z sub 2. Or I should say, here we go with modulus. Or, sorry. No. Here we go. Right. Okay. And so, using this to show why this, how this identity works, basically, what happens if I pick minus 1 for both values? So let z sub 1 be equal to minus 1 and z sub 2 also be equal to minus 1. Right, then z sub 1 times z sub 2 is equal to 1. Okay, and remember that by this example we did yesterday, the log of z sub 1 times z sub 2 then is log 1, which we found to be the multiple values 2 pi n I, right, where n is some integer. And of course, log of minus 1, so log of, say, z sub 1 is equal to log of z sub 2, since they're literally the exact same thing, which is log of minus 1. But what is log of minus 1? This is, we found this to be 2n plus 1 pi I, right? Okay. All right. But then, if that is the case here, right, then if I am looking at, say, the values, so when n is equal to 0, right, so if I take principal values here, right, then in that case, the values I'm taking would be taking log of z sub 1 times z sub 2. If I take n equals 0, this would be 0. And this would make log of z sub 1 and z sub 2 equal to pi I. So then log of z sub 1, for instance, we'll say that's the one I chose. The log of z sub 1 is equal to pi I. Okay. Then how do I define this? How do I do this in a way that makes this property that I've circled up here hold? Well, I've chosen log of z sub 1, z sub 2 to be 0. Log of z sub 1 here is pi I. So I want to choose this log of z sub 2 in a way that makes this work. So I don't actually want it to be equal to pi I, because then I would have pi I plus pi I, so I'd have 2 pi I, which is not going to make this work. This left-hand side is going to be 0, taking the principal value here. And then if I take the value of log z sub 1, defined from this to be pi times I, right? 1 times pi I. Then what do I need to do to make that expression work? Like, what value do I need to choose here? Well, I need to choose something that adds to pi I to get 0. So I need minus pi I. Okay. I need minus pi I for this to work. Okay. Right. And so this is what I'm saying when I'm saying that if you actually take the principal value, you don't quite get exactly this expression, right? So if you take the principal value, so taking principal log what do I get instead? So I have principal log of 1 is equal to 0, and principal log of minus 1 is equal to pi I. So then log of z1, z2 in this example is equal to 0, and log of z1 plus log z2 is equal to pi I plus pi I, right, which is 2 pi I. Okay, for the exact same numbers, z1 and z2. Okay. So what that means is, going back to this expression, this is going to be sometimes true when I replace this with, when I replace just log with its principal value. It's not always going to be true. So for instance here is an example where it's not going to be true. Okay, so one of your next homework exercises is going to involve this. Okay. Okay, so we also have some other familiar expressions coming in a similar way. So if we don't take principal values here, if we're just looking at log, so log of z sub 1 over z sub 2 can be thought of as log of z sub 1 minus log of z sub 2, interpreted in the same way. So I'm not going to go too much into that. So same reasoning, okay, works here. All right. Another useful expression is to think of z to the n as e to the n log z. Okay, where n is just some integer. All right, so this is an integer power of a complex number. Okay. All right. It turns out, so this is easy enough to see just by the definition of these things, but what about when I take powers that are, say, fractional powers, right? So one that we're, of course, interested in immediately is, what about taking nth roots of z in terms of the exponential function and logarithmic function? So what about z to the 1 over n? Well, it turns out that so long as z is not 0, I can write this thing immediately as e to the 1 over n log z. Okay, so this is for n being in the natural numbers, right? So 1, 2, 3, 4, and so on. Okay, and so if this is actually going to work here, based on what we know about nth roots of complex numbers, what is going to have to be the case here? Okay, well, this thing necessarily needs to be multi-valued, right? It needs to have n values here, right? That's what I know about nth roots of complex numbers. Okay, how does this work? Well, let's take z in polar form with its principal value for its argument. So this is r e to the I capital theta here. Okay, so that's the principal value of its argument. Well then, what is e to the 1 over n log z? What is that? Well, this is e to the 1 over n times the natural log of r modulus of z plus I times capital theta plus 2 pi k all over n, or times 1 over n. Okay, where k is some integer. Okay. But then, what is this? E to the 1 over n times natural log of r. I can move the 1 over n to the exponent of r. So this is e to the natural log of r to the 1 over n. And I'll write that again. So this is e to the natural log of r to the 1 over n plus this expression, I times capital theta plus 2 pi k over n. But now splitting this up using the exponent rule, this is e to the natural log of r to the 1 over n. That's just r to the 1 over n, which is the nth root of r, right? So this is the nth root of r times e to the I times theta, or big theta, over n plus 2 pi k over n, where k is some integer, n is some natural number. But what is this? This is exactly the nth roots, right? So this is exactly the nth roots of z. So when I write this, of course, I'm talking about the set of nth roots, right? I know there's n of them in general. If z is non-zero, there's n of these things, and so this is, in fact, exactly what I thought it is. Okay. This is useful because in a lot of analysis situations, when you want to deal with an exponent like this, it is better to involve the exponential functions. Okay, Yekta, I was looking at your question here. What I see. So if you have more questions, just let me know. All right. So that's that. In fact, we're going to immediately do this in order to talk about exponentiating a complex number to another complex number. Okay. And so the idea here is how do I exponentiate? So exponentiating a complex number to another complex number. Or complex exponents. So the idea here is the following. So what if I have a complex number z, right? And so let's let z be a complex number. Okay, z not be equal to 0. And let c also be a complex number. Okay, then what do I mean when I say z to the c? Okay, so what do I mean when I say z to the c? What I mean is I want to interpret this as e to the c log z. In fact, this is going to be my definition. So when you see this symbol, you can think of this as simply notation. And what's actually going on is I'm defining this symbol by this expression. Okay. The reason why this is nice is now I don't have to do any further work in showing some basic properties of this because I already know it from properties that we've earlier shown of the exponential function and now this log function. Okay. So we know how to do this when C is complex numbers that are either just integers or like 1 over a natural number, right? So we already know what this looks like, right? When C is equal to n, that is, it's just an integer, or when C is equal to 1 over n, right? We know both of these cases. We just saw that. Okay, but now what if C is something else, right? So what if C is actually a general complex number? So how do I talk about this? Okay, so I want to find what is I raised to the minus 2i. Okay. How do I take a complex number and raise it to some other complex number? Well, by definition here, how I would handle this is that this would be e to the minus 2i times the log of I. Okay. Now, I need to compute what log of I is. So log I is the natural log of the modulus of I, which is 1, right, plus I times pi over 2. Right, there's my principal value, plus 2 in pi. Okay, that is rewriting this, since natural log of 1 is 0, this is 2n plus 1/2 times pi over 2, or actually, no, sorry, so this is just times pi, I, where n is an integer. Right. Okay. And so, what is I to the minus 2i here? Then I to the minus 2i is e to the minus 2i times log I, which is this set. That's 2n plus 1/2 times pi I. So I have 2i times I. So that's, minus 2i times I. So that's minus 2 times minus 1, because I squared is minus 1. So this is 2 times 4n plus 1 pi. So this is e to the 4n plus 1 pi, right, where n is some integer. So these are my values of I to the minus 2i. So I want to note a couple of things here, right? So note, first thing to notice is that exponentiating complex to complex can have multiple values. In fact, this is typical, right? So it is typical that these are multiple valued. So this is multi-valued. So I to the minus 2i is multi-valued. And in general, we can make the statement that this is going to be multi-valued. Okay. Secondly, I want you to note that in this particular example, although we took a complex number and raised it to a complex number, these numbers are all real. Now that's not always going to be true, but in this case it is, right? Okay. All right. So that's one example of what it means to exponentiate complex number to a complex number. Okay. And these are some ways how this can be different, maybe different than you expect. Okay. What about, say, um, what about considering the reciprocal, right? So 1 over z to the c. Okay, how can I think about this thing? Well, this is 1 over, just by definition, this is 1 over e to the c log z, which, using the exponent rule, that 1 over e to the something is e to the minus that thing. So this is e to the minus c log z, okay, which is, by definition, z to the minus c. And so the usual way of thinking about exponents is behaving when it comes to this algebra is true. So in our notation, right, just from definition, this is true. Okay. All right. And so, for instance, using, again, the numbers from our example here, so say 1 over I to the 2i, right, is equal to I to the minus 2i. Thus, from the previous example, one over I to the 2i is actually e to the 4n plus 1 pi, right, where n is an integer. Since this was exactly what we computed, I to the minus 2i. That is what we computed in the previous example. Okay. Okay. So let's look at a branch of the log and use that to actually compute derivatives. Right. So this is the, if you understand what it is I'm doing here, then you'll understand exactly how we're going to go forward when we talk about why we want to introduce a branch of a given complex valued function, and what it is that we're doing when we do that, right? So the idea here is I have a complex. So I have a multi-valued function that is complex, and we'll call it, we'll even just call it like f of z, right? But it's multi-valued, right? So it's not the usual function in the strict sense, okay? So it's a multi-valued function f of z. If I want to do calculus stuff, right? And when I say calculus stuff, the thing that should pop into your head is like computing derivatives, right? So computing derivatives is the thing I want to do. So I want to talk about this, okay? So I want to discuss this thing, okay? But it's a multi-valued function, right? Discussing this thing requires what? So discussing this thing requires analyticity, right? Or requires the thing being holomorphic or regular, whatever word you want to use here. Okay, so this requires this thing to be analytic, okay? Well, how do I make this thing analytic? It's a multi-valued function, so that's not going to be analytic, right, if I don't do something to it. So then the idea is I specify a branch of f of z. Okay, just to bring back this definition one more time, a branch of a multi-valued function is any single-valued function that is analytic in some domain at each point of z, and it matches with the values of little f that I started with, okay, in that domain. So this is not just some random analytic function. It is an analytic function that is equal or takes on the values of little f in that domain, okay. And so, if you like, you can think of specifying a branch as specifying like an analytic part of the function in question. Okay? In such a way that it's continuous, even better, it's analytic there, and it's not multi-valued, it is single valued. Okay? And so what this is single valued and analytic. And so we are good to go to compute this thing. So that's what we're doing, all right? And that is how this is going to proceed. For the rest of the course, this is how we're going to deal with this thing. And if you take a course in complex analysis in grad school, the same exact thing is done. Okay, so if you take like a graduate level complex analysis course, this is how you deal with these things. Before you start doing computations like that, you deal with this potential nastiness of branches. Okay, my streaming software acts like I am having connection issues. I'm going to type this in chat. So I want you all to let me know if the video starts buffering or is slow, because my streaming software is saying that my connection is bad. So please let me know if things are stuttering or you can't, if things are cutting out or something, because I'm not going to be able to see that in real time, at least not without a delay. There's like a good like 20-second delay that I wouldn't be able to see. So please let me know if the stream starts cutting out or something. All right, so you can let me know in chat. Okay, so going back here, I want to specify a branch for this function. And so I want to do that because I want to talk about, for instance, how to compute the derivative of this exponential function, raising complex number to a complex number. All right, so that's what I want to know. Okay. So let's do that. So if I take z to be in its polar form, so r e to the I theta, and alpha is any real number. This is good because, of course, in doing this, you're including, say, the principal branch, if you wanted to do that. Then my log z function, of course, is the natural log of r plus I times theta, where, as usual, r is positive, and theta is strictly between alpha and alpha plus 2 pi. Okay. Okay. So then this is a branch of log z. So this is single valued and analytic, okay, in this domain. Okay, so in this specified domain, we are good to go here. Let me check, make sure no one's screaming about stream quality, because I keep getting these notifications for it, but it seems like everything's going all right. Okay. Okay. All right. So then, the point, right? The point. When we use this branch, instead of just the entire log z function, when we use this branch, this function that we defined, z to the c, which is e to the c log z, because we're using this branch, log z is single valued and analytic, and so now we are doing a composition of analytic functions. This thing is single valued. The function e to the z is single valued and analytic. And so what is it that we're doing here? Well, this function itself is single valued and analytic, right? So it means it has a derivative, right? So then the derivative of this branch of z to the c is given by g dz of z to the c. Of course, by definition, this is just d dz of e to the c log z. Here I can use the chain rule, of course. So using the chain rule, this is going to be e to the c log z times the derivative of c log z with respect to z. And from previously what I've computed there, right, d dz of log z is 1 over z. So this is c over z e to the c log z, right? But then, of course, what does this mean here? Well, I can rewrite this expression as, if I'm careful here, I can write, say, z as e to the log z. Right. The other direction was the thing that I didn't always have. I had to be careful here, right? So log of e to the z could be multi-valued, right? That was something that I had to be cautious about. But e to the log z was z, okay, without question. And so rewriting z as e to the log z here, this is going to be c times e to the c log z over e to the log z. Okay. And so this is c times e to the c log z minus log z, using this property of the exponential function again. Factoring that out, this is c e to the c minus 1 times log z. What is this? Right. So by definition, though, e to the c minus 1 log z is z to the c minus 1. So this is c z to the c minus 1. Oh. Oh. So this is actually very nice, right? So this tells me that actually this power rule for differentiation follows the exact same power rule as if I was using like a natural number here, right? Okay, so that's pretty amazing that it works out in the same sort of way. So just rewriting our result here, the derivative of z to the c, right, where these are both complex numbers, right? It's complex valued z exponentiated to complex number c. This is actually c z to the c minus 1. Okay, where, of course, the modulus of z is taken to be greater than 0, so then I can't do this for z equals 0. That's a branch point. And arg z is strictly between some alpha and alpha plus 2. Or, sorry, plus 2 pi. Okay. All right. So this is the derivative of a branch of that thing. Okay. So similar to before, the principal value of z to the c is obtained by replacing log z with the principal log. Okay. So principal value of z to the c is equal to e to the c capital log z. Right. And we can actually compute the derivative of this on the principal branch. So the principal branch, of z to the c is, of course, exactly what you expect. It is modulus of z greater than 0, and the argument of z is strictly between minus pi and pi. Right. All right. And so now you're seeing this pattern of how we treat exactly these sorts of things. Okay. And so let's do a couple of examples, then we'll move on, and maybe I'll relegate some others to homework. Okay, and so first example is what is the principal value? So find the principal value of minus I to the I. Okay, so what is this? So first of all, this principal value of minus I to the I is defined to be, it's z to the c, where I'm taking principal log here. So this is going to be e to the this is going to be e to the I times principal log of minus I. Okay. What's the principal log of minus I? So this is natural log of the modulus of minus I, which is natural log of 1. All right, so this is natural log of 1. Okay. Plus I times the principal argument here of minus I, which is minus pi over 2. Right, so this is minus I times pi over 2. Okay. All right, and so putting that here, this is e to the I times ln of 1, which is 0 minus I pi over 2. And so this is equal to, this is 0, and this is I times minus I pi over 2. So I times minus I is just 1. So this is e to the pi over 2. This is the principal value here. So a lot of times you'll see this written as PV. So PV of minus I to the I is equal to e to the pi over 2. Okay, and that's the principal value. All right. Okay, another example is the following. So let's write the principal value of, find the principal value of, say, z to the 2/3. Okay. Well, the principal branch is given by taking principal log, right, in the definition. So the principal branch is given by the following. This is, so z to the 2/3 is equal to e to the 2/3 log z. That is principal log z. So I can express this, of course, as e to the 2/3 times, again, just remember, principal log z is natural log of the modulus of z, which I'm just going to go ahead and write as r. Okay, plus I times the principal value here, capital theta. Okay, this is our normal way of writing this. So this is 2/3 times natural log of r plus I times capital theta here. Okay, so rewriting this, this is e to the 2/3 ln of r plus I times 2/3 big theta. Okay. So then moving 2/3 to the exponent of r here, because this is just natural log, so of course I can do that, right? And rewriting this, this is r to the 2/3, which I could write as r squared, or the cubed root of r squared. So this is the cubed root of r squared times e to the I times 2/3 theta. I can use Euler's formula to rewrite this. So this is equal to, well, maybe I'll just go ahead and say, since I'm looking for the principal value for some particular z, in order to write that out in general, the principal value of z to the 2/3 is equal to, this is cubed root of r squared times e to the I times 2/3 big theta. So this is equal to, using Euler's formula, this is cubed root of r squared times cosine of 2 theta over 3 plus I times cubed root of r squared times sine of 2 theta over 3. Okay, and this function then is single valued and analytic, so this is analytic. When I say analytic, you can just assume that it's single valued. So this is analytic in the domain specified by my modulus being greater than 0, and this principal argument being strictly between minus pi and pi. Okay. All right. So that's just yet some more to add to your arsenal, right? So we are slowly building our arsenal of complex functions in order to be able to talk more expansively about calculus stuff that we want to do to them, right? And so we have talked about polynomials, rational functions, we talked about the exponential function, log function, and now exponential function. So what have we talked about? So we talked about polynomials, p of z. We talked about rational functions, p of z over q of z. So that's analytic wherever q of z is not 0, right? Okay, we've talked about e to the z. We've talked about log z. Right? We have now talked about z to the c. So I want to keep going here. What's next? What do we fill in next? So if you're trying to do an analogy with what you did, right, viewing this starting from like algebra and going toward calculus, what's some other things you want to, maybe you didn't go in this order exactly, but next on the list should be trig things, right? Sine z, cosine z, right? All the trigonometric stuff. Then what? Well, then maybe we talk about actually something we could have already talked about, hyperbolic sine and cosine, sinh and cosh, right? And so on. Okay, so we're going to keep going from there. All right, in fact, talking about sinh and cosh is going to be particularly nice for us because you're going to see that the way that we're going to talk about sine and cosine is going to lend itself pretty easily to talking about hyperbolic sine and cosine, right? If you've seen those things before. Okay, and so, how about trig functions? So we want to talk about trig functions, sine z, cosine z. Right? And from these, we will talk about the rest of them. So, of course, we already know Euler's formula, which tells us something nice about what e to the I x is, right? So e to the I x is cosine x plus I sine x directly from Euler's formula. Of course, e to the minus x, or minus I x, right, is cosine x plus I, minus I sine x. You can use this, you can use the fact that cosine is even, sine is odd here, right, to immediately write this out. Okay, so this is a minus. All right. And thus, if we look at e to the ix, say minus e to the minus ix, okay, this is just subtracting this from this. What do I get? This is equal to 2I sine x, and e to the ix plus e to the minus ix is equal to 2 cosine x. So, in particular, we can actually think of sine x as being e to the ix minus e to the minus ix over 2I, and cosine x as being e to the ix plus e to the minus ix over 2. And now it becomes clear to you what I was talking about when I said this is going to lend itself easily to talking about hyperbolic sine and cosine, because notice that this is very, very similar to how hyperbolic sine and cosine are actually defined, right? As real valued functions anyway. Okay, and so what is the idea? To define, right, the functions sine z and cosine z by the similar formulas for generic z. Okay, so sine z is defined to be, so let me put my little colon there. So sine z is defined to be e to the iz minus e to the minus iz, okay, over 2I. And cosine z is defined to be e to the iz plus e to the minus iz over 2. So this is my definition of sine z and cosine z. Okay. Now, unlike having to deal with the nastiness of taking branches and stuff, which is very important, I'm not implying that, like, you know, you have to avoid that stuff. In fact, you shouldn't even try to avoid that stuff. You should embrace it because it's completely unavoidable. But the nice thing about these is that they are linear combinations of e to complex number. Okay, they are linear combinations of entire functions, right? So note, sine z and cosine z are linear combinations of entire functions, e to the iz and e to the minus iz. These are both entire. That doesn't take too much to show. Okay. So these are both entire functions. These are linear combinations of these entire functions. And so sine z and cosine z are entire themselves. All right, so no branches required here. These are entire functions. This meshes actually with exactly what you kind of expect or how you expect this to go, because sine and cosine are kind of two examples of your canonical extremely nice functions of a real variable. And just like, you know, e to the z turned out to be a really nice function of a complex variable, sine z and cosine z are also very nice. Okay. Okay. And so, actually computing the derivatives here is not so bad. In fact, so we want to compute the derivatives of sine z and cosine z. Now that we know that they're entire, they're analytic everywhere. So note further that if I compute the derivative of e to the iz, what is that? Well, this is I e to the iz, right? And the derivative of e to the minus iz is minus I e to the minus iz. Okay. then what is d dz of sine z? We know what we think it should be. Let's go back to our definition carefully. What's this derivative? Knowing these two things. Well, if you are careful here, I'm going to get e to the iz minus I e to the iz. So that's plus I e to the iz. So let's just write that out here. So this is going to be I e to the iz minus I e to the minus iz all over 2I. There's an I in common here. So this is I e to the iz plus e to the minus iz over 2I. The i's cancel, and we have e to the iz plus e to the minus iz over 2. Hey, that's cosine z, right? Okay. So using similar reasoning, so not only do I have that the derivative of sine z is exactly what I hope it is, it's cosine z, using our same definition here. The derivative of cosine z can be found using similar reasoning here, that this is minus sine z. Hey, we're happy. What does this tell us once we compute this? This tells us that using these definitions, right, because we just defined sine and cosine to be this, it tells us that using these definitions was the right choice, right? This was the correct thing to do here. Okay, this is very strong evidence that what we have defined is exactly behaving like sine and cosine that we're used to. Okay, so just directly from these definitions, we can deduce a few properties that are also familiar to us. So, for instance, sine is odd, right, in the sense that sine of minus z is sine z. You can deduce that yourself just directly from the definition. And cosine of minus z is equal to, sorry, this is minus sine z. What am I doing? And cosine of minus z is just cosine z. Okay. Lastly, e to the iz is actually cosine z plus I sine z. So we have Euler's formula even when z is a complex number here. Okay. So if z is a real number, this is just Euler's formula, but this is Euler's formula for complex z as well. Okay. So many of these, I'm not going to list them all, so many identities involving sine and cosine carry over. So this includes angle sums, angle differences. This includes double angle identities. So just a few. I'm not going to exhaustively list these. So like sine of, say, z1 plus z2. This is given by the familiar angle sum formula. This is sine z1 cosine z2 plus cosine z1 sine z2. Cosine angle sum is a little different. So if you remember, cosine angle sum is cosine z1 cosine z2 minus sine z1 sine z2. Okay. We have the usual double angle formula for sine. So sine of 2z is 2 sine. Okay, cosine of 2z is cosine squared z minus sine squared z. Okay, and we have the usual relationship between sine and cosine, where if I shift sine by pi over 2, right, so sine of z plus pi over 2 is cosine z, and sine z shifted in the other way, so sine of z minus pi over 2 is minus cosine z. So there's more than just this. So these things are periodic, of course. Sine z squared, the Pythagorean identity, right? Sine z squared plus cosine z squared is equal to 1 still. And so on, right? And so on. So a variety of identities that you can imagine here coming in the usual way. So they work out in the usual way. So I'm going to stop here. I have like a couple more kind of basic functions I wanted to talk about before we talk about kind of the meat, which is coming in the next chapter, which involves integrals. But the idea here is that this builds us a nice solid base of a bunch of example functions. Your next homework that I'm going to assign here in a little bit, so by this afternoon I'll have posted it, and it'll be due sometime on Friday or Saturday. So it'll be due basically, before your midterm that I post this week. This the idea here is that we're going to have a big base of examples here. This homework is going to ask you to work through a bunch of details, basically filling in some of the details or working with some of these functions so that you're more comfortable with them, because we're going to forge ahead with our analysis bit. We're going to be doing computations for the next, the last of the course, right? We're kind of at the halfway point now, so we're going to be doing computations for the last half of the course involving these functions, and so it's important that you are comfortable dealing with them. Okay, so anyway, we'll talk more about that tomorrow. Screen is very blurry, can't read. Okay. Yeah, let's see. This last page of notes was not clear. See if so I'll see how it is. I'll see how it is when it is uploaded. So once it gets fully uploaded, I'll see if it's really like unclear, it's completely blurry or whatever. And if it is, then I'll just begin tomorrow's lecture by going over these, so that at least you'll have captures of them. So I'll begin tomorrow's lecture by going over the last couple pages of notes, so that at least they're on camera and clear. Okay. All right. So anyway, yeah. Hopefully that's. I don't know what was going on. The whole stream, it was acting like my connection was bad for some reason. So hopefully it's not too bad. Like I said, I'll have a look at it here when I edit it here in a second before it gets uploaded. So hopefully that's fixed. If not, like I said, tomorrow in lecture I'll go over those pages. So sorry about that.